Welcome back to the final part of this tutorial series. In this part, we'll be looking at simple sentiment analysis using embeddings. For most text classification tasks, fine-tuned machine learning models will do better than embeddings because they have been meticulously tuned and trained on problem-specific data. There is training data with the correct answers and classifications, and the model is trained to predict the correct answer by seeing lots of correct answers. But what if we do not have any training data? We can use zero-shot classification to classify with zero labeled training data using ChatGPT embeddings. In this last part, we'll be working with a Jupyter notebook. This will allow us to easily display the graphs in line with the code and have a nice visual representation of our pandas data frames. Don't worry about this file, we'll create something like this in a moment. And if you don't like to use Jupyter notebooks, you can just use regular Python and insert the same code, but you'll occasionally need to insert a print statement in your file to see what we're doing, and your print output will look a little bit less pretty is all. I won't go into depth on Jupyter notebooks here, but I will explain the bare basics you need to know. So if you've not used Jupyter notebooks before, I would encourage you to follow along and take this opportunity to explore them. So for those new to Jupyter notebooks, assuming you're working with VS Code, you'll need two things. And if you're already using Jupyter notebooks, you can obviously skip these two steps. First, you need to pip install Jupyter. Now, I'm not actually going to run this because I already have it installed. And then last, you need to look for the Jupyter extension in the Extensions tab and install this extension, which has almost 70 million users, so it's quite popular, as you can see. Once you've done that, you should be good depending on the configuration of your system. Now, a Jupyter notebook very basically just allows us to chop our code up into blocks, which we can run one at a time. Unless we restart our notebook, the kernel executing our code will be kept alive between running cells, also keeping variables in memory. So say we have multiple code cells here. So in one cell, we could define variable hi. This is some text. And I'll just run this using Python. It's starting a kernel for us. And then in the next cell, we could print a variable and we see, hi, this is some text. In fact, we can often skip the print statement altogether, as just stating variable here will also return, hi, this is some text, which is one of the nice features of notebooks. We can just see the content of variables in between and then continue coding in the next cell. Okay, that's enough introduction. Let's get started. For this part, we'll be using the same database we've used for part 4 of our tutorial, where we had ChatGPT generate SQL queries to answer our questions about the database. You can download the file for free from this same address we've used before and extract the zip file anywhere. The file has two versions of the data inside. One is called database.sqlite, which we used for part 4 of the tutorial series, and the other one is called reviews.csv. For this part, we're going to be using the CSV version. So go ahead and grab it and copy it to your folder, reviews.csv, and I'm going to be renaming it to gxreviewsdatabase.csv, sticking with my alphabetical naming structure. And as you can see, it has lots of data, but these are the same reviews we've worked with before. Now let's create a new file, and I'll call it ga.datapreparation.ipynb, which is the extension for Jupyter notebooks. It's quite long. That's how you make a new notebook file. And VS Code will automatically recognize and open it in the Jupyter Notebook editor, which is sort of built in for VS Code. If you're using a regular Python file, you can just call it ga-data-preparation.py instead. In the top left, you can click code a couple of times to add some code blocks for us to work with. You can also add markdown for notes and markdown in between, but we're not going to be using this. In the first code cell, we'll put our imports, and note that the decouple and config parts are slightly different. Oops, I accidentally added a breakpoint. Because the notebooks need a slightly different setup for this to work. So just make sure you type it in this manner in the notebook. And if you're in regular Python, use the way we used in all the previous tutorials. The other imports are all familiar by now, and we define a couple of constants up top, like the embedding model and the name of the input database, and the output file name we'll use to store the embeddings. The output file does not exist yet, but it doesn't matter, it'll be auto-created. A very quick reminder for those new to Jupyter Notebooks. On the left side of each cell, you'll see an arrow. If you click on this particular cell, it will be executed and the variables will stay in memory and be available amongst different cells. If you want to start fresh, you can restart your notebook. I haven't actually run anything yet. But if I run, you can see we have restart here, which will restart all the cells and clear all the variables. So we have a fresh kernel now and nothing is run yet, and you can also click run all to just run every single cell in your file all at once. Okay, that's it for the basics. Now let's actually code up some data. In the first line, we use pandas to read data from a CSV file, just like the previous tutorial. We specify the database name as the first argument, or the CSV file. Then the columns we want to use, which is summary, text, and score, which means we ignore all other columns in the data except for these three we've defined. And the final argument is the number of rows we want to read. I'm going to limit it to 500 because the data set is really massive. But if you're very worried about the number of OpenAI tokens you will use, you could set it even lower to like 100. The next line may look a little bit confusing at first glance if you're not familiar with pandas, so let's read it from the inside out. Here we basically have a Boolean expression. Data frame in the column of score does not equal 3. So if the review has 1, 2, 4, or 5 stars, this will return true. But if it has 3 stars, it will return false. Now this code will run for every single row in the score column and return either true or false. Then we're setting the data frame to now be the data frame with the index of, and then we're passing in all these booleans for every single row. Every row that evaluates to true will be kept in this data frame, and every row that evaluates to false, so had a 3-star review, will be thrown away or filtered out of this data frame. So just the Boolean expression will keep all the rows that evaluate to true. And we only have the 1, 2, 4, and 5-star reviews left in our data frame because we want to do binary classification, only classifying positive and negative reviews. So we'll get rid of the neutral reviews for now to keep it simple. In the third line, we add a new column to our data frame called sum and text, or summary and text. And it's just a concatenation of title plus data frame summary, content plus data frame text. So we're just concatenating all the text data in a single column. Then the df.head just prints the first 5 rows, or the head of our data frame. So let's go ahead and run it, and we can see we get a nice representation. This is one of the advantages of using a Jupyter notebook. It's very good at printing out data frames. So you see the score. We have the summary, the text, and then the summary and text together, which we just created. And these numbers up front are an ID that's generated by Pandas itself. We did not put this here, and we can also get rid of it or ignore it. Now that we have a data frame with only the data we want, we'll need to generate embeddings again and save them somewhere before we can start analyzing the sentiment and doing stuff with it. In a new cell in your Jupyter notebook, write the following function. And it's going to be mostly the same. We define the global variables for the number of tokens used, the number of embeddings generated, and the total number of data rows in our data set. We can use dataframe.shape0 for this, which is actually going to give us the number of rows. This is a pandas method. Then we define a function called getEmbedding, which takes an item as input and returns the embedding for that item. Inside the function, we use the global keyword to access the global variables and increment them as appropriate, just like we did in the previous tutorial. We also print a progress message for every 10 embeddings generated, just like we did again in the previous tutorial. So this code is basically the same. As this is the last part of this tutorial, I'm not going to make you extract this into a separate folder and file again. We'll just copy and paste it for now. But if you're going to be reusing it, obviously to make it into a separate function in a separate file somewhere. Now go ahead and of course make sure to run this cell so the function is stored in memory. Otherwise we won't be able to use it. And now we'll use this function to generate embeddings for our dataset. So we'll add a new column, embedding, to our data frame we've been using so far, and we set its value to the summary and text column after a function has been applied to it. So we take the summary and text column and apply a lambda. For each row, it takes the item as input. It runs our getEmbedding function with the item passed in. We just declared it up here. So this function is going to return the embedding, which is going to be the content of the embedding column. We then use pandas to save the data frame to a CSV file again, skipping the index, which again is just this number up front that pandas generated. We don't need it, so we set the index to false. And then we print our success message again and dataframe.head, so we'll get to see the first 10 rows after this finishes running. So go ahead and run this cell, and you'll see the output just like the previous version we made. So this is going to take a while. I'm going to let it run and I'll be back in a moment. Okay, so it's finished running. We got our success message and a representation of the data frame, which has our score, summary, text, summary and text together, and our embedding column. Perfect. And you'll also have this review embeddings.csv, which is new and has all our embeddings data. So we have everything we need to get started. We have our data prepared and we're ready to do some sentiment analysis. So to keep things organized, I'm going to be doing this in a separate file. Go ahead and save and close the previous file and create a new Jupyter notebook called gbclassification.ipynb. Now open it up, and I'm just going to press the code button a couple times to give us some cells to work with, because I'm lazy and I like to just make a lot of cells all at once. Now we'll add our imports, Pandas and NumPy are familiar by now, and naturally we also import OpenAI and the decouple module. Again, notice that we do this differently than we did in the first 5-6 parts of our tutorial, just because Jupyter Notebooks requires this slightly different syntax to work. We also import classification report and precision recall display from sklearn.metrics. Now, if you're missing a particular module on your computer, you may need to pip install sklearn or whatever other module it's complaining that you're missing. So if you run into that problem, just install whatever you're missing and you'll be good to go. Then we import cosine similarity, which is used to compare again the similarity of different embeddings, and we import get embedding from the OpenAI embedding utils, which is just a shortcut function to get an embedding for a specific text. Below we declare our embedding model, database name, and a threshold as constant variables so we can use them throughout this file. The threshold refers to the threshold we'll use to classify a review as either positive or negative based on the similarity. We'll be able to play around with this value later to find the sweet spot for the greatest accuracy. So go ahead and actually run this cell. It can be easy to forget sometimes when using Jupyter Notebooks. And then you wonder why it's not working. Okay, it's importing all this stuff. And then in the next cell, we'll go ahead and read up some data. First, we read the CSV file as always and load the data to the pandas data frame. Then we select the embedding column, and again we have to evaluate the arrays back to Python lists, and then we have to evaluate them to NumPy arrays to allow for more efficient comparisons. Then we add a new column to our data frame called sentiment, which is just a copy of the score column, but we replace every 1 and 2 with negative and every 4 or 5 with positive. So we're only left with 2 values, positive or negative, because we want to do binary classification. And then we're going to set the data frame to be a copy of our data frame, which only has sentiment, summary and text, and embedding, as these are the only 3 columns we'll need for now. And then we'll print the head, the top 5 lines, just to see what we have. So we have positive review, good quality dog food, and then we have the embedding, and this one is negative, not as advertised, and we have the embedding again. Now let's move on to the next cell. It will contain a single function, which we'll go over in parts. This function will test the accuracy of classification labels, outputting a precision recall curve, which is just a graph showing the accuracy of our predictions. This will allow us to test labels such as positive and negative, or more complex labels such as positive product review and negative product review, to see which best match positive and negative review embeddings. The idea of this is that we test the embedding for a term like positive product review against the embeddings of the actual reviews in the database. If a particular review's embedding has a high similarity to the embedding for the string positive product review, then we can assume there is a high similarity in meaning, as in this is likely a positive product review. Our function will have the ability to take any labels we pass in, so we can test different sets of labels and see which give us the highest accuracy. We also made the sentiment column in our dataset, which contains the correct answers. So therefore, we'll be able to compare our predictions based on the embeddings with the correct answers in the sentiment column and see how good our accuracy is. So let's get started on this function in a new code cell. First, we define our function, evaluate classification labels, which takes the labels as an argument and type hints that this should be a list of strings. We also take the model and threshold as arguments, both of which will default to the constants we defined earlier above. Then we simply have a multi-line string, which is just a comment for ourselves on what this function does. It's just an alternative way of making a comment, and it's just for our own reference. Then we get the test label embeddings, which means one embedding for the positive review label and one for the negative review label. We use the getEmbedding method provided by the OpenAI library, calling it for each label in the list of labels, which is this list. So for every single label in the list of labels, it's going to call getEmbedding, pass in the label, and the engine is just the model, which is just the embedding model. And it's going to put these embeddings, which is just going to be two embeddings, one positive and one negative, in this list, which we catch in test label embeddings. Now we'll continue below inside of the same cell. Oops, it's got to be like this. And inside our evaluate classification labels function, we define an inner function of label score. This function takes two arguments, the embedding for a particular review and the two test label embeddings. So it takes a reviews embedding and it takes test label embeddings, which is a list of two embeddings we can generate using this. Then we get the positive similarity, which we have to run the cosine similarity function, comparing the review embedding to our test label embedding at index 1, which is going to be the positive embedding. And then we have the negative similarity, which is running the cosine similarity again with the review embedding against the test label embedding at index 1, which is the negative 1. And then we return the positive similarity minus the negative similarity. So if the positive similarity is very high, then this is going to be a high number. But if the negative similarity is very high, then this is going to be a negative number. So based on the value of this return, we can see what the prediction will be for the positive or negative sentiment in relation to this particular review. Okay, so now that we have the label score function, which is an inner function of the evaluate classification labels, we're going to continue below. Then we use the apply method on the embedding column of our data frame. And we will apply a function to each row in the column. We pass in a lambda function, which takes the review embedding as an argument and calls the label score function we defined earlier, passing in the review embedding and the test label embeddings, which we defined here. So for every single embedding, it's going to compare them with the positive and the negative review and then get the average score and store it in a variable we name probabilities, which is outside of our data frame, but it doesn't matter. Then we're going to say that predictions equals probabilities dot apply, which is another lambda, and it will take this score from probabilities in every single row, and it will return positive if the score is higher than the threshold, which we could play around with later, and else it will return negative. So this is going to make the predictions binary, either positive or negative. Okay, still continuing on with this same function, We will use the classification report method from sklearn.metrics to generate a classification report which will compare the predictions we just made with the data frame sentiment column, which again has the correct answers. So it's going to see how many of our predictions are actually correct. Then we're going to print this report. And then in addition, we will use the precision recall display from predictions method, which is going to display a graph for us based on the sentiments or the correct answers, the probabilities, and then we just have a label positive here. And here we just select the axis and set the title to precision recall curve for test classification labels. We don't need to print this graph or call print on it as we're in Jupyter notebooks, so it will call this automatically for us. And your entire cell should now look like this. We have the function which takes the arguments, gets the test label embeddings by getting the embedding for the positive and the negative label in this list. Then it has a function to calculate the label score of the test embeddings versus the review embedding for one particular review. We actually run this function above for every single embedding in the data frame. Then we turn these numbers into either positive or negative and call this prediction. Then we get the classification report. We print this report and then we get another nice graph. Notice that we're just testing stuff here and we're not actually adding our predictions to the data frame yet. We just want to test which labels are most effective. So this will allow us to test different labels. So go ahead and run this cell. So the function is actually loaded in memory. You can see a number next to it, so it has ran. And now we can use this function to test different labels and see which labels give us the highest accuracy. So we can test what labels we should be using. So first, let's test the similarity if we just use positive and negative as our labels. So very simple labels here. Now if we run the cell, we'll see a nice report here. And this will show us the accuracy of our predictions. And we can see that we have an overall accuracy of 95%, which is pretty good. We can also see that the precision for the positive label is actually 96%, which means that 96% of the time we predict a review is positive, it is actually positive. The recall for the positive label is 99%, which means that 99% of the time when a review is actually positive, we predicted it as positive. The F1 score is a combination of precision and recall, and it is 97% for the positive label. The support is the number of times the label appears in the dataset, which is 409 for the positive label. And the same goes for the negative scores, but we can see the accuracy is lower on the negative reviews. At this point, it will be up to you to play with the threshold between positive and negative and the evaluation labels to get higher accuracy. So let's try a set of more descriptive labels and see if we can get higher accuracy. Okay, so we're going to run the classification label evaluation function again in our next cell. And note that each cell has its own output, so we can easily compare this. And this time we've used much more descriptive labels, a product review with positive sentiment and a product review with negative sentiment. You can see our accuracy increased significantly to 98%. You can also see a big difference in the graph. And the precision and recall for the positive label are both 98% and 100% respectively, and the precision and recall for the negative label are both also significantly higher than before. This is just because the labels are more descriptive and thus more accurate, Because remember that this is not a machine learning algorithm, but a comparison of similarity between strings. So we compare the similarity of an embedding of this sentence with the similarity for a reviews string. So we're just comparing embeddings with each other. We did not train any type of model for these classifications. Now let's go to the next cell and write a function to add our descriptions to the data frame so we can take a more detailed and visual look at exactly what the predictions are. This function takes our chosen classification labels as argument and the model for generating the embeddings, which again defaults to our constant variable defined at the start of the file. The string comment is just for our own reference again, and we get the embeddings using the list comprehension that we used above. This inner function is also a copy from above. Again, if you're going to be making this into some kind of reusable module, you might want to merge these two functions together as they're very, very similar. But right now we're just using this for demonstration, so we just did a sneaky copy-paste. Then we'll get the probabilities again using the exact same method as we did above, and we then take these probabilities and apply a lambda function to them, which will take each score as input and evaluate positive if the score is above the threshold or negative if it's below the threshold. And this time we store the result in a data frame column called prediction. So again, this function is mostly copy-pasted from above. But to keep this tutorial simple and easy to follow along, we won't be refactoring all of this, and we'll just sort of copy paste it for now. That's a nice piece of homework for you to implement later. So finally, in the next cell, we'll put the following code where we'll actually call our function we defined above, and we'll pass in the labels we tested as being the most successful, the descriptive labels. This is just a set option method that Pandas provides, and we just want to display as wide as possible because the data frame will be quite wide. You don't have to really worry about it. It will just make our output look slightly nicer. Then we make a copy of our data frame, which we call print data frame, which simply drops the embedding column. Again, we don't need to see it in the final results because we can't read the embeddings anyway, and it will save space on our narrow screen so we can see more details. And then we simply print the 30 lines of the head. Now, I need to make sure not to forget to actually run this function cell before we call it. Otherwise, we're going to get some kind of name error. And now let's run it. Okay, so let's take a look at our results. And we can see that most of them are correct. Positive, negative, positive, positive, negative. And we have one here that doesn't match. All the others are all matching. Negative and positive are all matching except for number 16 as well. And there's only 2 reviews in this set of 30 that do not match. Let's have a look here. So it seems like the embeddings got confused by the root beer extract, which is labeled as good and adds positive words to this review. But it's not the actual product being reviewed in this review, as any human intelligence would obviously point out. So this user is doing a good job to confuse any sort of AI by adding positive words for a product they're not actually reviewing. So this is sort of understandable. It predicted positive where it's actually supposed to be negative. And let's look at the second problematic review, which is number 16. And it seems like this is actually user error. The embeddings are not wrong here. This is clearly a positive review as the user loves eating them. and the title of poor taste and the user rating of negative do not match their words, and the user likely made some kind of mistake writing this review. Maybe they wrote a lot of reviews in a row and they pasted something in, they mixed something up, and the embeddings picked up on this. So the embeddings are actually correct. This is a positive review and the label is actually wrong on this one. All the other review sentiment predictions are spot on, so there's actually only really one mistake in these 30 first results. That's pretty impressive for only using embeddings and doing classification without any dataset specific training data. So you can play around with the threshold and the labels to see if you can get even higher accuracy, but I'm pretty happy for now. Again, if you have a massive production grade environment, you'll need to look into a vector database to store the embeddings instead of CSV files, because it's going to get very huge if you have a massive project. But yeah, that's it for this tutorial series on ChatGPT function calls and embeddings. I hope you thoroughly enjoyed it and learned a lot. And it was my honor and pleasure. And I hope to see you soon in the next tutorial series. Until then, happy coding. Dirk van Meerveld signing out.